Hello, everyone. Thank you for joining us today. My name is Andrew Yarwood. I'm the Marketing Director at Brooks Bell. In way of introduction to this webinar, over the last few years, we've seen significant changes in the hull and machinery landscape. The growing size and complexity of vessels has led to a sharp rise in both incident severity and claim values. In fact, claims in 23 and 24 exceeded 50 million. That's a 22% increase compared to pre-pandemic averages. We've also seen a marked rise in high-value incidents, particularly in fires and explosions, highlighting the need for more robust, high-quality support across the industry. As a trusted name in the maritime surveying world, in investigation and in expert witness services, Brooks Bell is launching a series of focused hull and machinery webinars to explore these evolving challenges and to share insights with the market. Our first session is led by Ray Lucas, a name many of you will already know. He'll be discussing engine room fires, a topic that continues to be a major concern. The presentation will last around 30 minutes. If you have any questions during the session, please use the Q&A link at the top of your screen. We'll address as many as we can at the end of the presentation. If you have any comments after the event, we'll be sending a feedback form out. We would welcome your thoughts on the webinar, on the market, and on your changing needs. So let's get started. I'll now hand over to Ray Lucas.
Thank you, Andrew, and my thanks to everyone joining this webinar on engine room fires. Your time is most appreciated. This slide just gives you some of my background. I was at sea for around 15 years before joining Brooks Bell in 92 and been there ever since. At Brooks Bell, we have collectively probably investigated hundreds of engine room fires over many years. For my part, I've investigated at least 30 or more engine room fires and others outside of engine rooms over my 33 years in the firm. These days, we often adopt a multidisciplinary approach, as will become clear during this presentation. So, with no further ado, let's start with an overview of what this presentation will be looking at as we navigate through the slides. Despite many and numerous guidelines for measures to prevent engine room fires, including SOLAS and IMO Marine Safety Committee MSC circulars, engine room fires continue to occur every year. Indeed, more than 1/3 of ship fires start in the engine room. And courtesy of an important article published by Guard P&I Club as recent as 13th February 2025, reference was made to the club having seen 5 engine room fires in the first month of 2025. Their experience between 2017 to 2024 was that 60% of ship fires originated in the engine room. From my own experience, the root causes are very often similar, remembering the fire is a consequence of other factors, not always the root cause or causes. During this webinar, we will look at those causes, including some case studies Brooks Bell have investigated, and we will review fire prevention measures. The benefit of experience in such investigations is, or at least should be, an appreciation of what can go wrong with engine installations that are not equipped and maintained with a fire prevention culture in mind. It will be no surprise to see that fuel and lubricating oils coming in contact with hot surfaces still cause the majority of engine room fires, mostly involving main and auxiliary engines or generators. Of the aforementioned 60% of engine room fires reported by Guard, some 2/3 occurred at the main and auxiliary engines and their turbochargers. So for this presentation, I'm going to concentrate on the predominance of oil fires involving diesel engines, consistent with the blue section of this pie chart, and then move on to why, in our experience, we tend to see more fires on the medium speed engines, in particular auxiliary diesel engines or generators, as opposed to large, slow speed main propulsion engines. Then we will narrow down even further to highlight a propensity of fires caused by failures within the low pressure fuel oil supply and return system, sometimes called spills, compared with the high pressure fuel injection systems. Now, this is not all new news, and such fires reoccur despite SOLAS and other guidelines issued many years ago, a summary which now follows. So new design rules were introduced in the SOLAS amendments of 2000 and implemented by 2003, as exemplified by this MAN B&W service letter to ship owners and operators dated January 2003, recommending the installation of jacketed double skin fuel pipes for high pressure fuel injection systems at the first opportunity. In 2009, guidelines for fire prevention engine rooms and cargo pump rooms were issued by IMO Marine Maritime Safety Committee in Circular 1321. Some of these guidelines are summarised in this slide, and I will be discussing more of them in more detail later. As regards the last item for hot surfaces, some may ask why the criteria is set above 220 degrees. Well, this is based upon the auto ignition temperature of the more lighter fuels, such as MDO, MGO, which have a minimum auto ignition temperature of 250 degrees. So a margin of safety of keeping any hot surfaces, such as exhaust systems, below 220. The heavy fuel oils have an auto ignition temperature of about 400 degrees C, and lube oils are about 320 degrees C. And remember that auto ignition temperature is the temperature which the substance will spontaneously combine with oxygen and burn without the need for an external ignition source. It is the vapour that ignites, not the liquid itself. Here we see a diesel engine fuel system which incorporates some of the SOLAS requirements. A double-skinned high-pressure fuel injection steel pipe with minimum joints and bends by having the pipe pass directly through the cylinder head to the fuel injector. These requirements have reduced the risk of high-pressure fuel system failures, but failures to the low-pressure system, i.e. the fuel supply and spill systems, have persisted, as we will see later. Here we see a double-skin fuel pipe, which also allows for the failure of the internal pipe to be detected by routing the annular space to a leakage tank with a float-type alarm. We will see later how other potential leakage points could be piped to such an alarm tank, for example, fuel oil filter containment enclosures. This is a water-solar medium-speed engine, the master type, which features the hot box design for enclosing the fuel injection pumps and pipework, which are also then located at the opposite side of the exhaust system, so good containment and well away from hot surfaces. The hot box can also feature a drainage system piped to a fuel leakage alarm tank. Now, over the years, I've seen more fires involving 4-stroke medium-speed engines and auxiliary diesel engines, including those on container ships, which tend to have 4 generators compared to, say, a bulk carrier with 3. For a large, slow-speed 2-stroke engine in the left-hand image, we see the fuel injection pumps circled are distant from the exhaust system and turbocharger. Only the high-pressure fuel injection pipe is nearby the exhaust system, but that pipe is double-skinned. For the generator engine in the right-hand image, note that the filters, again circled, are in fairly close proximity to the turbocharger. Indeed, MSC 1321 recommends as much distance as practicable between fuel filters and hot surfaces or other sources of ignition, but we are still not seeing that implemented in all engine designs. Another factor is if the generator engine is using marine diesel fuel oil, which has a lower auto ignition temperature than the heavy fuel oil, which burns the 2-stroke engines burn. Here's a closer look at the filters on the Yanmar engine we looked at in the previous slide. Again, note the proximity of the filter to the turbocharger. Compare that with the filter unit on the Cummins engine, with the filters coloured in red, well away from the turbocharger. It can be seen that the filters for the Yanmar engine have silver-coloured heat insulation covers, which may also offer some anti-splash containment, so long as the covers are always in place after cleaning the filters. We will see later that a better arrangement would be to have the filters still insulated, but also fully enclosed in a sheet metal box. Returning to the difference of fires caused by high-pressure systems with double-skin pipes and the low-pressure fuel supply and spill returns, we see the problem in these numbers: 50% of failures in the low-pressure system compared to the high-pressure system. This is important because intuitively an engineer may consider the high-pressure fuel system to be the greater risk, but awareness should always be directed towards the low-pressure fuel system as well, which appears to pose a significant, if not greater, risk of fuel escape and fire. Now let's look at some of the reasons why. So we have fatigue, vibration, pulsations, chafing, that's rubbing of pipes against each other or structures, lack of brackets for security, and so forth. Now, fatigue does not mean that the pipe or equipment is tired. Rather, in material science, fatigue is the initiation and propagation of cracks in a material due to cyclic loading. It can be low-stress high cycle or high-stress low cycle. This failure mechanism is often caused by incorrect tightening of pipe flange bolts or vibration due to lack of pipe security. Tests done some years ago, as shown in the right-hand image, showed that during each fuel injection stroke, high-pressure pulses are reflected back into the low-pressure fuel supply and spill pipes. The pressure during such pulsations can be several times more than the nominal pressure of the low-pressure system. The cyclic nature of these fuel pulsations, low supply pressure and then high peaks, favours fatigue and the initiation of fractures due to tensile stress and failure unless the pipes and fittings are properly secured. This applies to the holding down bolts for fuel injection pumps and bolts for fuel pipes flanges. We'll now see some examples from cases investigated by Brooks Bell. This was a failure of a small bore fuel oil spill pipe on a diesel generator, which allowed an escape of fuel onto the turbocharger and a major engine fire. Metallurgical examination confirmed fatigue failure of the pipe, and the root cause was vibration due to missing brackets. Another example of failure, fatigue failure, this time with the holding down studs for a fuel injection pump. The left-hand image shows the normal configuration of the pump with a stud and its nut labelled as an example. There are 4 such studs, one at each corner of the pump housing. The centre image shows another pump for which the studs have failed and the studs and the nuts are missing. One was found in the ashes you see in the right-hand image. This pump was then repeatedly lifting off the camshaft, resulting in an escape of fuel from the low-pressure fuel supply pipe, which impinged on exposed hotspots at the turbocharger. And this was the result of the fuel escape, a major fire. The other generators were inspected, and you can see exposed exhaust piping in the centre image, and fuel leakages and a lack of covers at the fuel pump gallery on the other side of the engine, a result of poor maintenance. This was another generator fire due to an escape of fuel from the filter assembly. The location of the filters is circled in the left-hand image, below the control panel, which you can see is collapsed. The turbocharger is just above the control panel. The right-hand image is a close-up of the fuel filter assembly, and you see a copper pipe for the differential pressure gauge indicator. The pipe is broken away from a coupling, the loose end of which is circled. This allowed the escape of fuel that came in contact with an exposed hotspot at the turbocharger. So a number of things wrong here. The pipe should be steel, as provided by the original equipment maker, and not copper, because copper wear hardens and becomes brittle and prone to fracture. Then note the poor installation involving a large loop and lack of brackets. There was also missing shielding from around the filters to prevent spraying of the leaked fuel oil. The left-hand image is a view of the same type of filters of one of the other 3 auxiliary engines. And note the proper steel pipes fitted. The right-hand image shows the renewed filters assembly which was fitted to the engine, which caused the fire. Again, all steel pipes, but still no shields. Unfortunately, I found the IMO Circular 1321 and class rules somewhat ambiguous on the use of copper in fuel systems. If you word search copper in MSC 1321, you will see it appears 4 times. Section 6 refers to pressure and temperature gauges, and at 6.1, headed design, it states that copper pipes, where permitted, may be joined by brazing, but solder connections should not be used. At 6.3, under inspection and maintenance, it says copper gauge piping is particularly sensitive to work hardening, and all gauge pipes and fittings should be regularly inspected and maintained in good working order. Then in section 7, under pipe fittings, it states at 7.14, dealing with design, all copper and aluminium brass pipes should be heat treated, annealed, i.e. that means softened after work hardening during installation, and fitted with sufficient supports to prevent damage from vibration. So far, it seems copper pipes are permitted, but then it says replacement with steel piping should be considered. Finally, much later at pages 14 and 15, which refers to the high-pressure pulsations in the low-pressure fuel supply systems, which I addressed earlier, under section 1.3, design considerations, and 1.3.5, it says fuel pipes should be of steel and support should be adequate to prevent fatigue due to vibration, and the support arrangement should also protect the system caused by high-pressure pulsations. Then it states copper and aluminium brass should not be used as their inherent work hardening characteristics make them prone to failure when subjected to vibration. So let me be clear. In my view, copper should never be used for fuel system pipework, regardless of the application, including instrumentation such as pressure gauges and pressure switches and sensors. Indeed, such small bore pipes present a jet-like nozzle when they fail, producing a spray with small droplets of fuel that will readily vaporize on hot surfaces and favor auto-ignition. While looking at the new filter assembly, which is the duplex type, meaning one filter is in use and one is a standby, it is worth mentioning that it features locking plates, the silver plate circled in the left image, which can only be removed by loosening a center bolt, which is also the vent. The right-hand image is a more clear example, also shows the locking plate and the vent bolt circled. So if pressurized fuel emerges from the vent, the engineer knows it is still online. My own view is that it's safer to only change over and clean filters when the engine is stopped and the fuel system isolated. We have experience of serious fires and personal injury when errors have been made while working on fuel filters with the engine running or stopped but not isolated. Some case study examples follow in the next slides. This was a fire involving generators in an engine room of a bulk carrier. Generator number 2 in the centre of the image developed a leak from the fuel filter, which is on the right-hand side of the engine, which then sprayed diesel fuel oil onto the adjacent generator number 3. At the exhaust system, on the left-hand side, there are potential ignition sources. The exhaust system, as I mentioned, and electrical devices. In container ships, there may be a similar arrangement, but with 2 generators in pairs, port and starboard of the engine room. And these are the images of generator number 3, which caught fire, which then spread back to number 2 generator. We can see the oil circulation pump at the bottom left and the exhaust turbocharger assembly. There's also some electrical distribution relay boxes and pressure switches. So some potential electrical ignition sources, but the actual ignition point was the exhaust system in way of the turbocharger. Here we can see the insulation on the exhaust on the left-hand image, where it comes from the manifold before it enters the turbocharger assembly. There is a gap in the insulation exposing bare metal of the exhaust pipe underneath. This was a similar incident when an escape of fuel from number 2 generator filter assembly impinged on the exhaust system of the adjacent number 3 generator, the fire then flashing back towards the fuel source, creating another fire at number 2 generator. Note that the duplex filter unit is partially enclosed in a sheet metal box to prevent the spray of fuel onto its own exhaust system behind the box. The turbocharger can be seen just above the filter. But there is no front cover on the box to prevent spray of fuel onto the adjacent generator or its exhaust system. The bolts had failed at the left-hand filter unit and the cover had lifted, allowing the escape of pressurized fuel. Note the engraved marking on the changeover cock, which indicates both units of this duplex filter were online. In this case, we were denied access to the broken parts of the bolts for metallurgical analysis, but given the condition of the bolts at the other filter unit, it's possible that bolts were defective. In the left-hand image, note the mismatch of bolts and studs. Same situation in the right image, with one bolt in the right-hand unit, which is circled, being apparently too long, requiring a spacer provided by the nut beneath the bolt head. It is unlikely these parts are original maker's parts or tensioned properly. Here's a view of one of the other duplex filter assemblies on the same vessel, again with no front cover in the left image. The centre image is a drawing we produced to demonstrate how easy it would be to make the shielding complete with hinged covers for access, and the drain could be piped to a float alarm. The internal surface of the box could also be lined with heat insulation material, and the filter manual instructions for changeover and cleaning, together with warnings to properly isolate the filters, could then be laminated and posted close by the box. One of my colleagues recalls one ship owner arranging for the retrofitting of complete boxes over the filters for the generators, and I think engine and filter manufacturers could exist with this arrangement. Now, there have been other cases involving confusion as to which duplex use of filter unit is in use online and pressurised, resulting in the release of pressurised fuel during opening of the wrong unit when the engine is running, or the fuel supply system has not been properly isolated for the stopped engine. The filter changeover cocks typically feature these T-shaped engravings to indicate which unit is online, which is on standby, or both are in use, as we saw earlier. So the standby unit is the one which has been isolated, cleaned, vented, and ready for use next time. But if not maintained properly, these markings can become obscured or painted over, introducing a serious risk, as we will now see in the next example. This was another case of an escape of fuel from a duplex filter assembly, in this case from number 3 generator spraying onto the exhaust system of the adjacent number 2 generator. This occurred as the engineer started to loosen the nuts at the left-hand unit, which is still wetted by fuel. The ring spanner used to loosen the nuts was still present. See the yellow note. Note the changeover cock lever with the white arrow is pointing to the right-hand unit. Intuitively, the engineer assumed that this indicated the right unit was online, so it was safe to open and clean the left unit. And that is not an uncommon arrangement, and may be the experience of some engineers attending this webinar. However, that was not the case here. The lever was pointing at the standby offline filter. As the nuts were slackened off, the cover partially lifted under pressure and the O-ring seal ruptured, allowing the escape of pressurised fuel, which sprayed on the engineer and the number 2 generator exhaust system behind him, which then created a fire, which then spread back to number 3 generator. Now, the manual for the filters did stipulate, however counterintuitive, positions for the changeover handle or lever for disassembly. So in this example, comparing the manual diagram with the green handle in the right-hand image being in the disassembly position for the left-hand unit, then the marking on the spindle, if any, would indicate that the right-hand unit was online and not the left. The left-hand image here shows the changeover cock for number 1 generator filters, but the markings on the spindle are only painted, not etched. Also, when the paint was removed from the spindle, number 2 generators, no etched markings were seen, was present. That's the right-hand image. Now, in this sad case, there were other factors involved, namely, although the engine was stopped, the fuel supply pump which served all 3 generators was still running, and the supply valve for number 3 generator was still open. It should have been shut, thus isolating the filters. Also, the filter vent and drain, had it been opened before starting to remove the cover, as was stipulated in the filter manual, the engineer would have realised the unit was still under pressure. Now, we've spoken a good deal about fuel and ignition sources, but now I show a good example of insulation on an exhaust system on this medium-speed engine. We have insulation around the pipes themselves and within the shielding. All very good so long as it's maintained, particularly after repairs such as exhaust leakages or cylinder head or turbocharger overhauls. Good maintenance practice should include the use of infrared laser thermometers or thermographic cameras to detect hotspots after repairs and routinely. Very often indicator cocks are not shielded. Here we see 286 degrees, well above the 220 limit. Such instruments as these can also be used to trace electrical hotspots at main switchboards, in particular high voltage switchboards and distribution boxes. Now let's look at some prevention of engine fires. We've seen examples of poor maintenance and repairs, so our starting point would be there, putting that right as a fundamental to prevention. I'll be coming back to routine tests and inspections, but we've also seen crew training is also fundamental to safe operation of the fuel systems. As for third-party inspections, it is important that inspectors have experience or at least knowledge of the root causes of engine fires, so they look at installations with scrutiny and an appreciation of the risks. For example, the incorrect and poor installation of copper pipes that we saw at the filtered differential pressure gauge in slide number 16 was present when that engine was inspected and tested at a class survey without comment. And how many times have inspectors checked the generation of a fuel filter is not fully shielded and not appreciated that an escape of fuel could impinge upon the exhaust system of an adjacent generator. Therefore, fire prevention audits may be considered by ship owners and managers using inspectors who have investigated engine fires. This approach was taken many years ago with MARPOL surveys to prevent oil pollution, including illegal discharges, with surveys being carried out by inspectors who had been involved in such investigations. There are many articles issued by insurers that use warnings and recommendations for fire prevention, and ship owners and managers should also ensure that they receive engine manufacturers' service letters, some examples of which we see in the next slides. This was a service letter from MAN in January 2012, and it spoke about the relocation of filters away from exhaust systems and insulation covers for pipes. Note the steel pipes. The pipes are steel, but still no full shields around the filters. In this image, there's this slide. This left-hand image was a service letter dated December 2016 from MAN recommending splash guarding around fuel pipe joints. The right-hand image is another service letter dated March 2017, this time recommending splash guards around the fuel supply and spill pipe connections at the fuel injection pumps. I said I'd return to routine inspection and tests, and here are some more details. I will not read out all of them, they largely speak for themselves, but I would highlight the non-use of copper for fuel pipes and consideration of having fuel filters fully enclosed in boxes with fuel oil leakage alarms and instructions for changeover and cleaning posted locally. These recommendations and others can be incorporated in the ship's planned maintenance system for the engine department. They can also be included in superintendent's visit report checklists. Summary. So, fire is a consequence, not the cause. The root causes can typically involve mechanical failure, poor maintenance, and so forth, and it is common that the SOLAS guidelines have not been followed in these cases. But I do think the IMO guidelines could be tightened up to make it clear that copper should not be used for fuel pipes and filters should be fully enclosed, and also consideration given to relocating the filter assemblies away from hot surfaces and other ignition point sources. These provisions and others could also be stipulated by ship owners and managers in repair specifications for refits and dockings, and also in new build specifications. Obviously, engine makers could also include these provisions and make recommendations for selling by way of more service letters. Root causes of engine fires typically involve engineering, mechanical failure, so very often a multidisciplinary approach is needed for proper investigations. And although today I have concentrated on oil fires and hot surfaces, we have investigated other causes such as hot works, human error, catastrophic machinery failures, and electrical failures. Again, these have often required a multidisciplinary approach, and sometimes investigative software tools such as 3D modelling of engine rooms, computation, fluid dynamics, and finite elements, all of which we have in-house and can use for fire modelling for fire prevention, and also use fire modelling for fire prevention and spread of fire and smoke. Indeed, this may also be the case for other fire investigations outside of the engine room, such as bulk cargo fires, ro-ro ferries and car carriers, including fires involving electrical vehicles and container fires, perhaps topics for other webinar presentations. Finally, I have listed some of the material I've referenced, in particular for this presentation, for which I'm grateful, but there are more articles issued by P&I clubs and other sources on engine fires on the internet. Thank you for listening, and I will now hand over to Andrew for the question and answer session.
Thank you, Ray, for that really insightful and informative presentation. It's clearly a topic that struck a chord as well with our audience today. We've had a few questions that have come in already. Remember, if you have something to ask, to use the Q&A button at the top of your screen. So let's take a look at what we've got in so far. Ray, is there a geographical hotspot where you are seeing more claims? And if so, where and why do you think that is the case?
No, not in particular. We've investigated cases globally in the USA and in South America and the Far East, and also in Europe and the Middle East. So it's I don't see a geographical connection between them.
Okay, thank you. Another question. Where there is no obvious cause, for example, a broken pipe, how do you go about identifying the source?
Well, to begin with, most of the cases we have looked at, there has been clues, like a broken pipe or some tools or welding equipment left lying close to the seat of a fire. But otherwise, if it's more complicated, if the fire has engulfed the entire engine room, and sometimes you get a flooding as well when seawater pipes and condensers crack, then it can become more difficult. So you tend to look for the most intense heat damage. So structures, steel structures and so forth, which have been warped by heat. If you can still see smoke patterns, that can help as well. But there can be confusing engines because you've got other fuel sources in other places, so you can get secondary fires. So it's looking for the most intense damage is the best clue. But it can be influenced by other things, other factors, such as the type of fuel and ventilation, etc., where there might be more oxygen in one area than the other. So those can be quite difficult. But for the most part, in my experience, there's usually been some activity or clue that can tell you where the origin fire started, and also from some witness evidence.
Thanks, Ray. Slightly longer question, this one. Someone's been good at typing this morning. As you said, negligence alone cannot be blamed, and engine manufacturers have more to do. I don't think there's enough collaboration between stakeholders regarding the prevention of engine room fires. How or who should take the lead on this going forward?
Good question. Yes, I think all the stakeholders, as I mentioned earlier, I think that the IMO guidelines could be more tightened. Why talk about copper pipes maybe being permitted and then not? That should be clear. They do have guidelines in EMS guidelines that talk about keeping the distance between fuel filters and hot sources and so on. That could be implemented better. And also what I mentioned about enclosures. But of course, the ship owners themselves have an opportunity to retrofit these systems with shielding around fuel filters, for example, and also cease the use of copper pipes. One of my colleagues, engineer colleagues listening here, was with P&O Shipping many years ago, and they removed all copper pipes from the engine room fuel systems and replaced with steel. So that kind of thing is in the hands of ship owners and managers. Of course, at source, engine designers could improve these matters as well by putting the filters in different places and not having copper pipes in any of the installations. And also, we could call upon classification societies to be more stringent.
Thanks, Ray. A few more. Got a few coming in. I have often seem to have cases where a fire in the engine room causes a blackout, which means the crew cannot use the ship's pumps to engage in firefighting efforts. Do you think these kind of firefighting systems should have backup generators based elsewhere on the ship?
Yes, and they do. The emergency generator is usually outside of the engine room and will be connected to a fire pump. And also there's a fire pump, a diesel-driven fire pump, very often in the forecastle of the ship. So there is backup systems already for those purposes.
Okay, thank you. Can you see any difference when it comes to fire damage or conditions in engine rooms that could lead to fires, dependent on their vessel type?
Not in the engine rooms themselves, no. The fires I said, the container ships, of course, might pose a bigger risk because they have more generators than, say, a bulk carrier. So we have 4 generators there because of the power supply required very often for reefer containers. So they need more generators. So there might be a factor there that you may have more risk.
Okay, just a couple more. Will the 220-degree guidance stand up to green fuels such as biofuels and the change to other alternative fuels, Is training for these new fuels included in STCW and firefighting courses?
Not that I've seen yet, no. So we may have to revise those tests and the temperature limit once those fuels start to become more in use. We haven't come across vessels using these ammonia fuels yet, or biofuels.
Okay, and one more. When the requirements regarding hotspots was new, my impression was that Class had this high on the agenda, but it appears that Class don't have hotspot survey high on their agenda today. What is your impression of that?
I absolutely agree with you. The only Class 3 society I've seen issue, and it was only a recommendation, was DNV, and that was many years ago. I think it should be mandatory to have the hotspots done with the generators running, at least the generators running at 80% power, and also it should also be done for electrical switchboards, in particular 6.6 kV high voltage switchboards.
Okay, thank you, Ray. No more questions in. We are 11:37, so not far off our half-hour mark. That brings us to the end of our first webinar in our H&M series. Thank you to everyone who's joined us today. Thank you very much to Ray for giving us the presentation. We will be hosting another session after the summer on stern tube bearing failure, so please keep an eye out for that invitation. And also, please keep an eye out for the feedback form. As mentioned earlier, we'd welcome your views on today's webinar and the market in general. A recording of today's webinar will be available on our YouTube channel. We'll also share the link on our LinkedIn page and our website. So thank you again for your time. We look forward to seeing you at the next session. Thank you. Goodbye.